So, as we are moving towards the single phase AC circuits, but as we know that the DC circuits and DC sources can also are also very important, and their importance cannot be neglected. So, first of all, we should know where the DC is applicable. So, it is used, its applications are in electroplating, charging of storage batteries, as in case of our mobile batteries and vehicles batteries, refining of copper, aluminum, electrotyping. Electrotyping is the when we produce the prototype of some metallic objects, that is included under electrotyping. Production of industrial gases by electrolysis process, you know. There is two electrodes, cathode and anode, and the DC power is obtained, and along with the DC power some industrial gases are there, principal tractions, etc. So the main benefits of both the AC systems and DC systems are known to us, and the good thing about them is that they are interchangeable. Okay, so DC can be converted into AC and AC can be converted into DC as per our requirement. So we can get the best of both the worlds. Okay, so we are aware of the inverters. So when the AC supply is not there, we can use these DC sources, which converts this DC into sinusoidal AC using inverters, using these DC batteries. Similarly, this AC voltage sources can be converted into DC sources using different type of rectifiers. So the if we are having any specific applications of DC, we can rectify the AC and use them. Okay, so another, its sources of DC are mainly battery, which provides the constant EMF, but the magnitude of the batteries and the secondary cells and the solar cells is less. So we go for the DC generators. Now, what are the reasons of choosing electrical energy in AC form? Is that AC generators have no commutators. So what is this commutator? Commutator is nothing but the mechanical rectifying device, or you can say mechanical rectifier. Okay, so these are placed in DC machines, DC motors and DC generators. So what does this commutator do? It converts that AC into DC. Okay, but the process of doing or the conversion is such that there is sparking involved. Okay, so whenever there is a sparking, there will be some burning of metallic and non-metallic parts, and it will produce the carbon black. So the surroundings of the commutator and the DC machines becomes contaminated. Okay, This is one thing. And also due to sparking, wear and tear increases. We have to replace the machineries which is or the parts which are associated with the commutator frequently. Efficiency also reduces. Okay, so because of these drawbacks of commutators, it cannot be, it is not a good option. So but the AC generators are also called alternators. So they do not have commutator, therefore they can be built in large units, big capacity. They can be run at high speeds, for example in turbo generators, and they produce high voltage such as 11 kV. So 11 kV is the general generating voltage in India, although in few advanced countries 16.5 voltage kV, 16.5 kV and 33 kV generation is also taking place. Okay, and also the construction and the operating cost per kilowatt is low in case of AC generators. Next is the that AC voltages can be raised or lowered using transformers. With the help of step up transformer, we can increase the magnitude of the voltage, and using the step down transformer, we can decrease the magnitude of the voltage. So this raising and lowering of magnitude of voltages in case of DC is a bit complicated process. We have to use choppers for that, and also these choppers are again not a very efficient machine. So in the AC system, transformers are very good machines. The efficiency of the transformer is easily achieved from 95% to 99%, whereas the efficiency of the DC machines, DC motor or DC generator, it is calculated as 65%, 70%. Okay, so we can say that AC machines are more efficient. Okay, another reason of the transformer being more efficient machine is that transformer does not involve any rotating parts. Okay, so this is also one of the reason. So AC induction motor is economical in initial cost and in maintenance. This is also a good thing about it. And AC motors are more efficient, and high transmission efficiency in AC makes the generation of electrical energy economical. Transmission efficiency is also good. Okay, so that's why we transmit the AC voltages at greater distances. As you know that Bhakra Nangal Dam, which is situated very far away from us, but still the power is transmitted from that power plants. And also if we mm, say distribution is also easy in case of AC system. And also since the AC system is widespread, so all the equipment, switchgear, machinery which are associated with the AC systems are easily available, they are less complicated and economical than DC. Okay, whether it is switches, circuit breakers, isolators, insulators, etc. And maintenance cost of the AC equipment is also less. This is also a good advantage. So next topic is our generation of sinusoidal voltage. So how this sinusoidal voltage or AC voltage is generated. So the principle behind it is that whenever there is a relative motion between the magnetic field and the electric field, the EMF is produced. Okay, so so when we talk of the relative motion between the magnetic field and the electric field, so either the magnetic field can be stationary and the electric field or the conductors, electric conductors are moving, or electric conductors can be stationary and the magnetic field is moving. Okay, or both the system are in movement, that is also possible. But another important point which I have mentioned here is that the relative motion, that is also very important, because the net resultant movement should be positive or negative, but it should not be zero. Okay. So either, so when we talk of the angular velocity of the rotor, so that angular velocity can be due to the movement of the conductor or due to the movement of the rotor. So where which application is used, this is to be known when we use small AC generators. Okay, at that time the generators which are being used have fixed magnetic field. Okay, which means that the north pole and the south poles are fixed, and the electric field, or you can say the conductor, assume that this is the rectangular coil which is placed between the, so if this is the rotor, this is the armature which is acting as a rotor. So let us assume that it is moving. It can move in either direction, clockwise or anti-clockwise direction. So when it moves, the flux lines which are coming from the north pole and it goes to the south pole, this flux cutting will take place. Okay, so based on this flux cutting, EMF will be generated. Okay, so this is the principle which is used in the small AC generators. Okay, so but in case of big or large size AC generators, what happens that our rotor is fixed. Okay, this is our rotor and this is the magnetic field. Okay, so this is our magnetic field, or you can say uh, north pole and south pole are there in the armature, and it is surrounded by the conductors or the coils. Okay, so here this is the large size AC generators. Here there will be movement of rotor or magnetic field. Okay, and conductors remain stationary. So here again there will be the relative motion between the magnetic field and the electric field, and hence there will be generation of AC sinusoidal voltage. Okay, so now we have to focus on the this EMF generation or the voltage generation in the sinusoidal case. So let us consider a rectangular coil of n turns rotating in anti-clockwise direction with the angular velocity of omega radians per second in the uniform magnetic field. Okay. So when we talk of the uniform magnetic field, what does we mean? That let us suppose that this is the our uniform magnetic field, and say here it is our north pole, here it is south pole. So the magnetic lines of forces or the magnetic flux is moving from north pole to south pole uniformly. Okay, so it is a uniform magnetic field. Okay, and we have assumed that a conductor is placed in this magnetic field. Okay, so this conductor is assumed to be rectangular coil, but we are more focused on its flux cutting feature. Okay, so let us suppose this is the conductor, and we are not drawing the three-dimensional uh, figure of it, else it will be like this. Okay, so but we are focusing on its top view. Okay, so when it is rotating, then obviously flux cutting will be taking place. So but we are more focused on its top view to analyze the angles well. And now the direction, so its direction is taken as anti-clockwise. Okay, and speed is omega radians per second, which is the angular velocity. Okay, and the direction is anti-clockwise. Why we have taken the anti-clockwise direction? Because the anti-clockwise direction is also the direction of positive direction of x-axis. Okay, so whenever we take the angles, if we are taking in the anti-clockwise fashion, it is the positive direction of x-axis, which you have studied in class 9th or 10th, I think. Okay, so it is convenient for us. Okay, okay, so let the initial position of the rectangular coil be like this. So in this position, when this conductor is placed in the uniform magnetic field, all the flux, the maximum flux is associated with it. Okay, and because the position of those flux lines and the rectangular coil are at 90 degrees to each other. Okay. So maximum flux is associated with it. So then we will study its movement in the anti-clockwise fashion, and also this conductor is having n turns. Number of turns are n. So that is also be taken into the consideration, because we know that the EMF produced is minus d phi by dt, but that minus d phi by dt is taken when the number of turns are 1. Okay, but if the number of turns are n, that at that time we have to take minus n d phi by dt. Okay, this you must have studied earlier as well. Okay. Okay, so and let the time is measured from the instant of coincidence of the plane of the coil with x-axis. So x-axis is taken as reference axis with respect to position as well as with respect to time. Okay, so we can say that at time t is equal to 0, that rectangular coil is placed either on the x-axis, or you can say parallel to x-axis. It's all the same. Okay, for our convenience we can say that it is placed on the x-axis. Okay, so at that time t is equal to 0 will be taken. So at this instance phi m links with the coil, or the maximum flux links with the coil. Okay, now let us assume that after the passage of time t in the anti-clockwise direction, the rectangular coil assumes the new position as shown. Okay, so with the passage of time t, what will be the angle which will be associated with this? It will be omega t. Okay, angular velocity is omega, so the angle which will be associated will be omega t. Okay, so this is shown here. In this position, the component of the flux along the perpendicular to the plane of the coil will be phi m cos omega t. Okay. So again, in earlier case also, when t is equal to 0 was there, we have considered the flux which was associated in the perpendicular direction to the rectangular coil. Again, we will consider the same, but now the magnitude of the flux will change. So what will be the new magnitude of the flux? It will become phi m cos omega t. Okay, so how this has taken place, let's analyze. So this is our conductor, and since the coil, rectangular coil, has moved to the position theta in the positive direction of x-axis, so its perpendicular direction, the flux which is associated in the perpendicular direction of the coil will also be shifted to the angle theta. Okay, so now this is the perpendicular flux. which is associated with the rectangular coil. So, this, now the perpendicular direction earlier was this. Now the perpendicular direction has also moved to the angle theta. So if now we draw the right angled triangle in this way, then what is the cos theta? Cos theta is base upon hypotenuse. So this hypotenuse is the earlier perpendicular direction, and at that time all the phi m or the maximum flux were associated with this. Okay, so now the cos theta or the cos omega t. Okay, now we can replace this by cos omega t is this base upon hypotenuse. So hypotenuse is this phi m. So we will get the base. So this base is phi m cos omega t. Okay, so this is what we have derived. So this is the perpendicular flux which is associated with the new position of the rectangular coil. Okay, now we can calculate the EMF easily. So next concept is flux linkage. What is this flux linkage? If we multiply the flux, linking flux by the number of turns, we get the flux linkage. Okay, so now what is the EMF? EMF actually, in a more refined language, we can say it is the rate of change of the flux linkage. Okay, so if we, and it is denoted by lambda. So if we say d lambda by dt is EMF, also you can put the negative direction. This is more appropriate. Okay, so now lambda is nothing but your n phi. Okay, so phi is now replaced by phi m cos omega t. Okay, so that is substituted here. So these n and phi being the constant comes out, and cos theta is, derivation of cos theta is minus sin theta. So this minus and this minus becomes positive, and again this omega comes here. Okay, so we get the EMF as minus, oh sorry, phi m and omega sin omega t. Okay, so all these three things can be clubbed to EM. So EMF at any instant. Okay, this is very important. EMF at any instant is, first of all, the instantaneous EMF. If something happens in an instant, it happens very rapidly. In instantaneous EMF is denoted by small letter e and in italics. Okay, so it becomes EM sin omega t, where EMF this. So this is the sinusoidal EMF which is generated by the AC generator. Okay, this is the complete derivation.